Hi, good afternoon to everybody. I'm Neil Mehta, and I'll be presenting our experience in profiling MatVec using OpenMP Offload on Intel Gen9 and compare its performance with a Volta V100. Um, just to begin, MatVec is a benchmark which is designed very simply to do a single task, which is to multiply a matrix with a vector and generate a vector. We use OpenMP 4.5 directives to achieve this, and we profile this OpenMP offload code on Intel Gen9 and compare its performance with the commonly available NVIDIA V100. The reason is we want to compare how and where Intel Gen9 performance can be improved in terms of compiler development as well as in terms of code development. The compiler that was used for this work was Intel DPC++ for Intel Gen9, and we use Clang 11 for V100. The problem size in each dimension was 1,000 elements. So we have a total problem size around 1,000 cross 1,000 cross 1,000. And the code has a 3 GB memory footprint on both these devices. The code very simply is broken down into three distinct compute hierarchies. In the first compute hierarchy, we have OpenMP target teams distribute. One thing to note here is that we have three multidimensional array, which are M, X, Y, and Z, which are instances of the array-MD class that we created. The essence of this class is that these arrays behave like multidimensional arrays, but the underlying structure holds all the data as a single block of memory. And DPTR, which is mentioned on line 2 here, is basically pointing to this memory block and has to be deep copied to the device memory. That's why we have the first copy which have objects MXY, and in the second copy we copy the base pointer. So this defines our first compute hierarchy, which is OMP team target teams distribute. In the second level, the team MatVec is called from the first compute hierarchy and has a second compute hierarchy of pragma OMP4. Similarly, a vector dot function is called from inside the team MatVec function, and this is the third compute hierarchy, which has pragma OMP SIMD. Now, as our keynote speaker mentioned in the morning, that OMP SIMD is not yet supported and will be supported from C++ standard 23. And so we created this with a view to benchmarking in future as well. And this is the general idea of the code. Now, before I go on to describe the performance and the profiling results that we have on these two devices, it's better to take note of the difference in the GPU architecture. What I've shown here is the architectural diagram of NVIDIA's V100. And on the first compute hierarchy level, it has something called SM, or streaming multiprocessor. There are total 84 streaming multiprocessors, out of which 80 are used on V100. And each SM launches a maximum of around 32 thread blocks. And so more or less you get around 5,120 FP32 cores per GPU when you're using V100 at its peak. In comparison, we have Intel Gen9, which is an integrated GPU architecture. And the compute resources are divided into 3 GPU slices, and each of those slices in turn have 3 sub-slices. A sub-slice has 8 execution units, and each execution unit has 7 threads. And so we have a total of around 504 threads per GPU. So roughly you can say that V100 has 10 times higher number of more or less threads being launched. And so performance has to be kept in with, you have to keep it in respect with these differences in the resources that are available. And so the time to solution of the data that we currently have On NVIDIA, the baseline, which is basically an OpenMP code run using just one thread, you have 11 seconds required for kernel time. Whereas on Gen 9, you have 275 seconds. When you implement the second compute hierarchy levels, the first two, basically OpenMP Team Target and OMP4, you get 2.17 seconds on V100, whereas 20.36 seconds on Gen 9. Again, as we should remember that there are 10 times higher number of threads on NVIDIA V100. So the performance kind of makes sense. As I previously mentioned, SIMD doesn't really do anything, and so the performance is exactly the same with some statistical variances, since the results are run for around 100 times for each measurement. So what exactly is happening? So we have work mapping hierarchy, and using metrics grid size and block size on V100 and work size global and work size local on Intel Gen9, we could kind of make out on what exactly is happening when we are running our benchmark code. And so we have the Pragma OMP target teams distribute, which is being mapped on the level of streaming multiprocessors. And since the problem size is n equals 1,000, it's being distributed to 1,000 on the first level of compute hierarchy. So it's being mapped on the level of subslices. That's kind of our conjecture at this point. On the second level, when we implement OMP parallel for, it's being mapped on the level of thread blocks, launching in a block of 128 threads every time we run team MatVec function. Similarly, we believe that the OMP Pragma OMP4 is being mapped to the level of execution units on Intel Gen9 and launched in a block of 32 threads. SIMD, when it comes, we would love to see how it takes use of the compute resources on either of the two machines. Just to give you a brief understanding of what Roofline method really leads to. So we have this particular plot where we have the HMB, or high bandwidth memory, peak bandwidth line, and it intersects with the peak compute throughput of any given architecture. The point at which those two lines intersect is called an elbow. And a line drawn vertically from that elbow line divides the roofline into two distinct regions. So that to the left of the elbow line region, you have memory bound kernels, and to the right, you have compute bound kernels. The kernels that are shown in blue here are capped by the memory capacity of our architecture, whereas the kernels shown in green here are capped by the compute throughput, peak compute throughput. The kernels shown in red, even though they are in compute regime, compute bound regime, are not really within 50% of either of the capacities. And so spending our energies more on optimizing these kernels would give the maximum return of investment. And that's the general idea of the roofline model. Ideally, you want all kernels to shift upwards and rightwards towards the compute bound region, because as we see from the trend, and if the trend indicates something, it's highly likely that the next generation of GPUs will have more improvements in compute resources compared to the memory resources. And that means that if your code is in compute bound region, you will get higher speed ups with better, newer hardware that is being implemented in the pre-exa and exascale machines. So how does our roofline look like? So here we can see that on NVIDIA V100, we have our kernel, which is roughly in memory bound region, but very close to the elbow line. And the kernel is not close to either the 50% of compute throughput, as well as it's not close to the high bandwidth memory or the DRAM bandwidth. So there is a scope of improvement, and we understand that this might not be the most optimized parallelization technique to use for OpenMP, but excuse me, our intent was to understand how OMP directives get mapped on the compute resources on each of the GPU. And this leads us to a very interesting outcome on Intel Gen9. We see that even though this particular kernel is not bound by the memory bandwidth on V100, it is memory bound between the DRAM bandwidth line. Now, notice that theoretically, a roofline cannot cross the bandwidth line at the level at which we measure the roofline. And we've measured this roofline at the DRAM level. Since it's crossing, we suspect that the EDRAM, which is a special memory used on Intel Gen9, is coming into the play, and which suggests that our performance is capped by the memory bandwidth. And also notice that the difference between V100 and the Intel Gen9 is that even if you were to improve the kernel on V100, you could make it faster by optimizing, whereas here the performance is severely capped by the DRAM line. And just to summarize, the profiles indicate that the expected differences in the performance between V100 are approximately 10 times as expected because of the difference in the resources. However, the kernel, even though the kernels are memory bound on both these machines, the benchmark code is bound by the EDRAM bandwidth on Intel Gen9, but not on V100. And so we believe compiler maturity plays an important role in how the code performs. And we need further development work in mapping using the SIMD directives. With that, I would like to thank the JLSE systems at the JLSE group at Argonne National Lab for providing us resources to use the code. Also, I would like to specify that the benchmark code is available at this GitHub link, and it has multiple versions, so you could use it for CUDA, Cocos, or other backends as well. With that, I would like to conclude my talk. Thank you. If you have any questions, I'd be happy to take them.